A live nuclear reactor, riding inside the belly of a bomber, once circled above Texas, shielded by 12 tons of lead and steel, watched by a nation gripped by Cold War dread. In the shadow of atomic optimism, America built the Convair NB-36H to test the dream of endless flight and airborne supremacy. Yet after 47 flights and 89 hours of reactor operation, this vision of unstoppable power was quietly buried. Why were we willing to risk the sky for a future that never came, and what finally brought the world's most dangerous aircraft back to Earth? In the early 1950s, the world's nuclear arsenal was measured not just in warheads, but in hours aloft. Within the bunkers and briefing rooms of Strategic Air Command, endurance became the currency of survival. General Curtis LeMay and his staff demanded bombers that could circle the edge of the Soviet Union for days, engines never cooling, crews always ready. The logic was plain. As long as American bombers remained in the sky, retaliation could never be preempted. But conventional fuel placed hard limits on this doctrine. Every gallon burned brought the aircraft one step closer to vulnerability. Tanker fleets and mid-air refueling bought time, but not infinity. Outside the military, the public mood was shaped by a different kind of optimism. President Eisenhower's Adams speech in 1953 painted nuclear power as the key to a new era, one where atomic energy would drive ships, trains, and even airplanes. Magazines and newsreels promised a world where reactors powered everything from suburban homes to commercial jets. In this climate, the idea of a nuclear-powered bomber was not outlandish. It was a logical extension of American faith in technology and the conviction that the future could be engineered into existence. For Strategic Air Command, nuclear propulsion offered a seductive answer. It promised a bomber that could stay aloft for days or weeks, effectively immune to the constraints of fuel, the promise of infinite loiter, of a machine that could outweight any enemy, became both a strategic imperative and a cultural symbol. Out of this convergence of fear and hope, the aircraft nuclear propulsion program was born, with the NB-36H as its first audacious step. In 1952, a tornado tore through Carswell Air Force Base in Texas, leaving behind a battered B-36H Peacemaker. The airframe, written off as unsalvageable, became an unexpected asset. Rather than scrap the damaged giant, the Air Force and Convair found opportunity in its ruin. The B-36's immense frame, 230 feet from wingtip to wingtip and 162 feet in length, offered the space and strength to carry not only a nuclear reactor, but the formidable shielding such an experiment demanded. The aircraft nuclear propulsion program took shape on paper first. In 1951, the Air Force awarded General Electric a contract to develop a nuclear propulsion system. The partnership pulled in Convair for airframe modification and Oak Ridge National Laboratory for reactor design. The plan was not to build an operational bomber, but a flying test bed, a machine that could answer with data and not theory whether a live reactor could be carried aloft and managed by a human crew. The NB-36H was conceived as a laboratory in the sky. Its mission was to carry a fully functional 1-megawatt air-cooled reactor, never connected to the engines, into flight, gathering data on shielding, crew exposure, and operational logistics. The reactor would ride in the aft bomb bay, separated from the crew by the full length of the fuselage, and a 12-ton shielded nose compartment. This was not a machine built for war, but for measurement. Built from the remains of a storm, and the ambitions of an era that believed every technological question deserved an answer, no matter the weight or the risk. The sheer scale of the NB-36H defies casual comparison. Its wings stretched 230 feet from tip to tip, wider than a city block. The fuselage measured 162 feet, a corridor of aluminum and steel running the length of a blue whale, with the tail rising nearly 48 feet above the tarmac. At maximum gross weight, the aircraft tipped the scales at 357,500 pounds. Every detail spoke to a machine designed to shoulder the burdens of a new age. 6 radial piston engines, Pratt & Whitney R-436E Wasp Majors, lined the trailing edge of the wing, their propellers spinning in deliberate synchrony. 4 General Electric J-47 turbojets, each tucked into streamlined pods, provided extra thrust for heavy climbs and high-altitude flight. This was the origin of the phrase, 6 turning and 4 burning. Yet for all this power, the most consequential mass on board was not an engine at all. Suspended in the aft bomb bay, the Oak Ridge Aircraft Shield Test Reactor, ASTR, waited in its armored cradle. The reactor core, air-cooled and compact, delivered a thermal output of 1 megawatt. At 35,000 pounds, it weighed as much as a fully loaded city bus. Air was drawn through the core and expelled aft, a direct cycle approach chosen for its simplicity and reliability. The reactor was never connected to the engines. Its only purpose was to test whether a live atomic heart could be carried safely through the sky. Each figure, wingspan, length, gross weight, reactor mass, was a measure of ambition and a reminder of the physical realities that shaped every decision. The NB-36H was not just an experiment in nuclear science, but an exercise in engineering scale, where every pound counted and every inch of space was pressed into service for a singular, audacious goal. Inside the forward fuselage of the NB-36H, survival depended on a barrier of engineered mass. The original cockpit was replaced with a sealed capsule, lined with 12 tons of lead and a rubber composite. This was not comfort, it was necessity. Each wall, every inch of the floor and ceiling, absorbed or scattered the radiation streaming from the reactor suspended far aft in the bomb bay. The windows, if they could be called that, were slabs of leaded glass up to 1 foot thick, distorting the world outside into a muted, heavy silence. Water tanks filled the voids behind the crew, their hydrogen atoms slowing and absorbing stray neutrons. A liquid shield in an airborne fortress. 5 people worked in that enclosure: pilot, co-pilot, flight engineer, and 2 nuclear engineers. Their world was pressurized, climate-controlled, and isolated by design. The nuclear specialists watched reactor gauges and radiation meters ready to trigger a shutdown if levels spiked. The flight engineer monitored engines and systems, all conventional, while the pilots navigated the long arc between Texas and the New Mexico test range. Meals and rest were rationed by the length of a flight. There were no bunks, no relief from the constant hum of machinery, and the knowledge of what lay behind them. Between July 1955 and March 1957, the NB-36H completed 47 flights, totaling 215 hours aloft. For 89 of those hours, the reactor was live. The shielding worked. Dose rates in the crew capsule remained within limits, but the price was weight and complexity. Every flight was a calculation. How much mass could be spared for safety? How much for endurance? The result was a machine that proved survival was possible, but only just. Every calculation returned to the same inescapable sum: weight. The NB-36H carried a reactor and shielding that together imposed a 47,000-pound penalty, mass that delivered no thrust, carried no bombs, and offered no operational advantage beyond survival. To shield the crew, 12 tons of lead and rubber transformed the nose into a bunker, while the reactor itself demanded its own armored cradle. The price for each hour aloft was paid in payload lost and performance sacrificed. Maintenance crews faced a different equation. Every inspection risked contact with activated surfaces, complicating even routine repairs. The air cooling system, chosen for simplicity, vented radioactive air aft, raising the specter of contamination in both the aircraft and its wake. In the end, the engineering verdict was clear. The airplane could fly, but only by surrendering the very qualities, range, payload, and flexibility that defined a strategic bomber. By 1957, the logic that had driven the NB-36H aloft began to dissolve. The Air Force canceled the nuclear aircraft program that year, as intercontinental ballistic missiles promised faster, surer retaliation than any bomber, no matter how long it could stay in the air. Aerial refueling, once a stopgap, matured into a permanent solution, and tankers like the KC-135 turned finite range into a manageable problem. The NB-36H was quietly retired, its final flight logged, its reactor powered down for the last time. In 1958, the airframe was scrapped at Fort Worth, leaving only technical reports and a few photographs as evidence of its existence. The fate of the Oak Ridge reactor core remains uncertain, likely dismantled, or stored under the protocols of the era. What endured were the lessons in shielding and safety, data that would shape future designs. The vision of atomic flight faded, but the knowledge gained did not vanish, it lingered. A silent legacy for engineers who would face new frontiers. Nuclear-powered flight remains a vision grounded by risk, not lack of ambition. As nations today revisit atomic propulsion for space and defense, the NB-36H reminds us, technological possibility is never enough. Safety, politics, and public trust still draw the flight path. The sky remembers every gamble.